Good morning. Today we discuss about the applications of Routh criteria. So in the last class we discussed about how the Routh arrays can be used to find the stability of any system. So in similar fashion, here this Routh criteria can be used in different conditions, like say find out if I want to find out say relative stability. So if I want to find out the relative stability, I can use the Routh criteria. I can use the Routh criteria. This is the one. And the second one is if I want to find out the range of values of k, range of values of k. K is nothing but here system gain, meaning for which values of this k is the system is going to be stable or unstable or marginally stable. So the range of values of that k, for which it is going to be system is stable, for which it is going to be system is marginally stable, or for which the system is going to be unstable. So these are the things which you can find out by using the Routh criteria. By using the Routh criteria, one is the relative stability, the other one is the range of values of k. Range of values of k. So we'll go one by one. So first is we'll discuss about the relative stability. Relative stability. Yeah. So the name says relative stability. Stability of any system with respect to some point, with respect to some point or some line. Say if I have a S-plane like this, if I have a S-plane like this, which is at S equal to 0, and the real axis, and this is the imaginary axis. Okay, so and I have say one more line which is at S is equal to minus sigma, at S is equal to minus sigma. So here if I want to find out the stability of the system with respect to this S is equal to minus sigma, with respect to S equal to minus sigma, in the sense this thing completely we are shifting this imaginary line, we are going to shift towards this side, means with respect, now this will become as the imaginary. So what is the relative stability with respect to this line? Relative stability with respect to this line S is equal to minus sigma. So in this case replace S. So when I want to find out the relative stability of any system with respect to a line, that line as S value, that replace the S value with the new, that is x minus 1 or x minus sigma. Say here I have given the minus sigma, S is equal to minus sigma, the sigma value may be 1, 2, 3, 4 and so on. So replace the S with x minus sigma and find the characteristic equation, then form a Routh array. After forming a Routh array, then we know how to evaluate the stability of a system after forming a Routh array. So now examine the stability of the system. That will give the relative stability with respect to S is equal to minus sigma. This is the one of the important applications. So in this, what we do is, if I want to find out the relative stability with respect to any line, so I am going to replace the S value with x minus sigma, then form the characteristic equation, then find the Routh array. After forming a Routh array, then we need to examine the stability as discussed in the previous class. Now coming to the second application, which is range of values of k. Second one, range of values of k. So here k talks about the system gain. K talks about the system. For which value of k, the system is stable Okay, or for which value of system is unstable, or we can find out for which value of system it is going to be marginally stable. Marginally stable. So these are the three things which you can find out by using this Routh array, the range of values of k, for which value of k, whether k is equal to 10 or 20 or whatever it is. So for which values of the k, the system is going to be stable, and for which value of the k, the system is going to be unstable, and for which value of the k, the system is going to be marginally stable. So the system gain values can be known to, to increase or decrease the system gain. So for the stability, or if it is unstable system, for which value of k it is unstable, then design a control system such a way that which is less than that k value, less than that k value. So likewise, we need to find out the range of k values, for which the system is going to be stable, and for which the system it is going to be unstable, and also for which value of k it is going to be marginally stable. So these are the three things which are going to find out using the Routh array. So we'll discuss one by one. Say for example, we'll take finding the range of values of k. One example we'll take so that we can understand. So find the range of values of k. Find the range of values of k so that the system having the following characteristic equation will be stable. See here the condition is asking for stable. So for which value of k, for the range of values of k, the system is stable. So for what values of k? So that is what is asking. So what is the characteristic equation is given? So characteristic equation is given as s into s square plus s plus 1 into s plus 4 plus k is equal to 0. So here he is not multiplied these terms, so we need to multiply these terms, and then we have to write the characteristic equation. So he has mentioned this is the characteristic equation. So first write the characteristic equation. So characteristic equation after multiplying. I can write. So s into, okay, first we'll multiply this inside terms. These two terms I will multiply. So s cube plus 4s square plus s square plus 4s, then plus s plus 4, right? So this is the one, and then plus k equal to 0. Then one more is if you simplify this, s into s cube plus 5s square plus 5s plus 4 plus k equal to 0. Then multiply this with s. So I'll be getting s to the power of 4 plus 5s cube plus 5s square plus 4 into s plus k is equal to 0. So now this is the characteristic equation which you have got. So now for this characteristic equation, I'm going to form the Routh array. Say Routh array. What are the coefficients we have? S to the power of 4, then s cube, then s square, then s to the power of 1, then say s to the power of 0. So I'll write the coefficients. 1, see, we can write as 1, 5. I can write the coefficients 1, then 5, that is 1 and 5 here. Then 5 and 4, here is 5 and 4, and here is k, and 0, nothing is there because the last is k, so nothing is, next is 0, we'll write. So what are the s square coefficient? 5 into 5, 25, minus 4. 25 minus 4 is 21. So 21 divided by 5. So I'll be getting 4.2. 21 divided by 5 is 4.2. Then 5 into k minus 0. So 5k only. So 5k divided by 5, I'll be getting k. And then this is 0. Then s2 power of 1 quotient. So yes, 4.2 into 4. That is 16.8 minus 5k. 16.8 minus 5k divided by 4.2. Then this into this, the remaining will become zeros. Remaining will become zeros. Then s to power of 0, that is the last coefficient. Generally, when we calculate, this has to come, k has to come. So this into this, 16.8 minus for this whole term into k minus this 0. This will become 0. 4.2 into 0 is 0. So only this into this divided by this. So leftover is k only. So leftover is k only. So I got k. So if I want to jet the system, see here he's asking for stability. So when I want to have the stable system, necessary and sufficient condition which has to have is all should be of the same sign here. So what is the sign which you have? Of course, the k should be greater than 0. So here there are two things which you can find out. This is 1 and this is 1, which is having the k terms. So this is the plus 1 plus 5 plus 4 point. So and this is in terms of k is there, and this is also, it is k only. So it should be all are plus plus plus, in the sense this also should be positive, this also should be positive to get the first column elements, to get the, this is the first column, because in the Routh array necessary and sufficient condition, if you have remembered in the previous class, the first column element should be have the same sign, then only we can say the system is said to be stable. So here if I want to have the same sign, this should be greater than 0 and this should be greater than 0. So what range I can write now here? So 16.8 minus 5k divided by 4.2 should be greater than 0. Of course k is greater than 0, of course greater than 0 from the last thing. So 16 point from this equation, inequality equation, if I take out the 4.2 that side, I'll be getting 16.8 minus 5k is greater than 0. Then if I take out this 16.8 greater than 5k, so if I take out the minus 5k to that side, I'll be getting, so if I reverse this equation, so inequalities, very importantly, inequalities, if I reverse this subject 5k this side and 16.8 that side, then it will become 5k is less than 16.8. So k is less than 16.8 divided by 5. So which is k is less than 3, then 3.36, 3.36. So k is greater than 0, k is greater than 0, and it should be less than 3.36. It should be less than 3.36. So I can write the range now. I can write the range. So k is greater than 0. So 0 less than k less than 3.36. So this is the range of k. This is the range of k for which the system is stable. For which the system is stable. So the statement should be written. So the range of k values for which the system is stable is 0 less than k less than 3.36. So this is how we can calculate the range of values of k for which the system is going to be stable. For which the system is going to be stable. Similarly, we can find out, say, a range of, say, one more problem will take. Where the second, other point will be given, that is the system is marginally stable or stable. So then find out the some unknown parameters like that. So we'll take one more problem on this. A system oscillates with a frequency of 2 radians per second. Find the values of k marginal and unknown. See here, p parameter is unknown, so p no poles are in RHS means the system is stable. RHS means right hand side, so no poles are in RHS. This statement says the system is stable. For the system is stable here, the system is stable. No poles are in RHS means that is in right hand side in the S plane. In the S plane, right hand side means this side, so no poles are existing here. So it means that it is a stable system, means all are lying on the left hand side. So left hand side is said to be stable. So that is the thing which he has given. Next we need to know what is the characteristic equation. For that he has written, he has given the block diagram. He has given the block diagram of a system. So then, so from this block diagram we need to find out the characteristic equation. From this block diagram we need to find out the characteristic equation. Here he has mentioned k into s plus 1 divided by s cube plus ps square plus 2s plus 1. So this is the thing, this is R of s and this is the C of s, and there is a unity feedback system. Nothing is mentioned in the feedback, then it is called unity feedback system. So for this minor loop, we know that what is the closed loop transfer function, that is C of s by R of s is equal to, we know that G of s by 1, and here is a if you look at this, this is a negative feedback system, so I can write 1 plus G of s into h of s. H of s is anyhow 1, h of s is anyhow 1. So here this denominator, whatever you get here, that is called as characteristic equation. That is what you can call as characteristic equation. So first find out the C of s by R of s. C of s by R of s, so what is the formula which according to the formula? So k into s plus 1 divided by s cube plus ps square plus 2s plus 1 divided by, I can write 1 plus k into s plus 1 divided by s cube plus ps square plus 2s plus 1 into h of s is 1. So that is nothing but is the closed loop transfer function. If I cancel out the denominators in the numerator and as well as denominator, so I will get k into s plus 1 divided by, so s cube plus ps square plus 2s plus 1 plus ks plus k. So this is the thing which you have got. So what is the characteristic equation from this? So characteristic equation, as I told, that it's the denominator, whatever you get that equal to 0, you'll get the characteristic equation. So what is mentioned is s cube plus, I'll rearrange the term here, ps square plus s terms are, there are two terms are there. So here 2s is there and ks is there. So I'll write bracket k plus 2 into s, k plus 2 into s. And constants also, there is two terms are there, 1 is there and k is also constant. So plus k plus 1 is a constant, k plus 1 is a constant, so which is equal to 0, So this is the characteristic equation which I have got from this. Now I have to form a Routh array. So form a Routh array. So this is the Routh array. Then what are the coefficients we have? So there is s cube, then s square, then s, then s to the power of 0, s to the power of 1, and then s to the power of 0. So I'll write, so these two coefficients, that is I'll write vertically downwards, so that is 1 and p. The second one I'll write k plus 2, and one more is k plus 1. So, and the remaining, of course, zeros, we have the zeros. So now this row we need to calculate, that is p into k plus 2, minus k plus 1 into 1, so minus k plus 1 into 1 divided by p, and then this p into 0 minus 1 into 0 divided by p, so this will become 0. This will become 0, then this also will become 0. Next, s to the power of 0 term, so this into this minus p into 0 is 0, so this into this divided by this will get k plus 1, so k plus 1. So now I got, so this is the value of in the first column elements, so from the first column elements, if I want to find out the marginal value of k, there should be existence of row of zeros. There should be existence of row of zeros. See here, very important point. For a marginal value of k, if I want to find out marginal value of k, then there should be existence of row of zeros. So here, if I make this one equal to 0, if I make this one equal to 0, what will happen? So this is 0, and this is also 0, and this is also 0. So it will become row of zeros. So equate this equation, that is p into k plus 2 minus k plus 1 divided by p equal to 0. So if I equate to 0, then there is the existence of row of zeros here. So then we can find out the marginal value of k. So if I write this equal to 0, then I'll get p is equal to, from this p is equal to, if I send to this 0, then p into k plus 2 is equal to k plus 1. K plus 1 divided by, so I am writing directly k plus 1 divided by k plus 2 is the p value. Okay. So, but still we need to find out the k value. So in order to find out the k value, right. So we need to write the auxiliary equation. So what is the auxiliary equation for the row of zeros? When you get the row of zeros, just a row above this 0 is called as auxiliary equation. So from this, what is the auxiliary equation? A of s is equal to p into s square plus k plus 1 into s to the power of 2 minus 2, so that will become s to the power of 0, that is equal to 1. So this is equal to 0, this will become auxiliary equation. From this, s square is equal to minus k plus 1 divided by p. So if I write this is equal to s is equal to plus or minus j root of k plus 1 by p. So as I told that the s variable is having the real part and the imaginary part, and j imaginary part. So here if you look at the imaginary part is always represent the frequency in the s domain. So the imaginary part, that is omega. So j omega. So whatever the value we have got here plus j into this represent the frequency. It represents the frequency. So what is the frequency is given in the problem? So the problem he has given the 2 radians per second. So square root of k plus 1 divided by p will become 2 radians per second, because it is this represents the frequency. So from this, squaring on both sides, I'll be getting k plus 1 divided by p is equal to 4. So from this, I can get p is equal to k plus 1 by 4. So I have this equation. Say this is equation 1, and I have this equation 2. That is, both represent the p values, k plus 1 by k plus 2, and this is equal to k plus 1 by k plus 4. So equating 1 is equal to 2, as the subjects are same. So they're making the right hand side equal. So that is, I can get k plus 1 by k plus 2, which is equal to k plus 1 by 4. So cancel out this k plus 1 on this side and this side. So taking the cross multiplication, so k plus 2 is equal to 4. Then from this, k marginal value is equal to 4 minus 2, 2. 4 minus 2, 2. So this is the k marginal value. This is the k marginal value, because we have found out the marginal value of k. For the marginal value of k, so this is our k marginal value. So whatever k you have substituted is k marginal value. So the k marginal is 2, and he is asking to find out p value also, right? So k marginal, for which value of system is marginally stable, is for the k value is 2. And he's asking for p is also, we know that p equation, p is k plus 1 by 4. So substituting the k value in this, so 2 plus 1 by 4, which is 3 by 4, 0.75. So I have got k marginal is 2 and p is equal to 0.75. 0.75. So this is how we can find out the range of values of k, and also for unknown values also we can find out by using this. And this is about second application of determining the range of values of k. Similarly, we'll go for the first application, that is relative stability of the system. One problem on this, one problem on this. So here, yeah. So determine the here both will be present in the same problem, that is range of values of k. Determine the range of values of k such that the characteristic equation, okay, which he has mentioned as s cube plus 3 into k plus 1 into s square plus 7k plus 5 into s plus 4k plus 7 equal to 0, which has roots more negative than. It means that is asking to find the relative stability for s is equal to -1. So it means that the roots which has the more negative than s is equal to -1 means which has more negative than -1, in the sense here the -1 is there. We need to find out the relative stability of this with respect to this line. Means we are shifting the s is equal to 0 line towards this s is equal to -1 line. So for this, what is the stability of the system? As well as find out the range of values of k. So range of values of k for the system is stable and all those. So here the two applications we have covered in this problem. We are finding the relative stability of the system by replacing the s with x minus 1, and then find out the new characteristic equation, form the Routh array, and determine the range of values. So now, replace s is equal to x minus 1. Then the characteristic equation will be replaced like x minus 1 whole cube plus 3 into k plus 1 into s minus 1 whole square plus 7k plus 5 into s is x minus 1, sorry, here is also x minus 1, and x minus 1 plus 4k plus 7 equal to 0. Now expand this a minus b whole cube. So a minus b whole cube is a cube minus 3a square b, then plus 3ab square plus 3ab square, then minus b cube b cube. So I am using the a minus b whole cube form and substitute in this a cube minus 3a square b plus 3ab square minus b cube. So expanding this x minus 1 whole cube, I'll be getting like this. Next, similarly, 3 into, of course, 3k plus 3 and x minus 1 whole square, a minus b whole square. So a square minus 2ab plus b square plus 7k plus 5 into x minus 1. Directly I can multiply. I can multiply, that is 7kx minus 7k plus 5x minus 5 plus 4k plus 7 is equal to 0. Now expanding this whole term, I'll be getting x cube minus 3x square plus 3x minus 1 plus 3k into x square, 3k into x square plus minus 3 into 2, 6kx, then plus 3k, then plus 3 into x square minus 6x plus 3, then plus 7kx, as it is I'm writing 7kx minus 7k plus 5x minus 5 plus 4k plus 7. At a time we will do all this. See, x cube terms, only one x cube term we have, so straight away we can write the x cube, only single term is there. So we'll combine all the x cube terms and x square terms and x terms and all those. So if you look at, I have only x cube term, right? Next, if I look at the x square term I have here, okay, and then I have here, okay, and then I have here, and anywhere else. Yes, there are three terms, that is we have minus 3x square plus 3kx square plus 3x square. So this minus 3x square, and plus 3x square will be cancelled out. I'll be getting 3kx square. I'll be getting 3kx square, x cube plus 3kx square. Now, so combining these x terms now, here is 3x is there, then minus 6kx is there, okay, then minus 6x is there, plus 7kx is there, plus 5x is also there. So if you look at this, 3x minus 6kx plus 7kx minus 6x plus 5x. So these are the terms which you have. So plus 3x minus 6x, it is going to be minus 3x, minus 3x plus 5x, it will become plus 2x. So I'll write plus 2x, then afterwards I'll write 6kx and all. So minus 6kx is there, plus 7kx is there. So what I'll write is plus kx. Later on we'll combine these two terms, okay, right? So now constants. So if you look at the constants here, okay, so here it is, I have minus 1. So here it is, I have minus 1, and here 3k plus 3k, okay, then here I have plus 3, okay, and here minus 7k, then I have minus 5, then plus 4k, then plus 7, okay. So if you look at first k terms, if you look at plus 3k minus 7k, plus 3k minus 7k, it will become minus 4k, minus 4k plus 4k, it will become 0. So k terms is not there. So I can cancel out this one, and this one. So now minus 1 plus 3, minus 1 plus 3 is plus 2, plus 2 minus 5, plus 2 minus 5 is minus 3, minus 3 plus 7, it will become plus 4. So I'll write plus 4 equal to 0. Now I can write this characteristic equation by combining these two terms also. So x cube plus 3kx square plus k plus 2 into x plus 4 equal to 0. This is the characteristic equation after replacing the s value with x minus 1. Now I need to find out the Routh array for this. So write the Routh array. So what are the terms which you have? X cube, then x square, then x to the power of 1, then I have x to the power of 0. So first two rows, taking the two coefficients, then I'll get the 1, 3k, then k plus 2. Okay, I'll write a little bit far. Okay, right. So here k plus 2, I'll write k plus 2, then 4. Then here nothing is there, means 0 will write. So the second row we can find out. The second row, 3k into k plus 2, 3k into k plus 2 minus 4 into 1, 4 divided by 3k. Then this will become 0, this will become 0. And x to the power of 0, so this into this divided by, minus 3k into 0, the second term will become 0. So only one term will be there, that is this into this, divided by this, then I'll be getting 4 here. So now if you look at the Routh stability, Routh's array, so if I want to judge the stability of the from the Routh array, we have the first column, we need to look into the first column element. So from the first column element, we know that there are two k terms. One is 3k, the other one is this one. So we need to have from the system stable. And if I want to say the system is stable, I have to have all the same signs. So this is +1 and this is also +4. So these two also should have the plus sign, means greater than 0. So what are the two things I can write here? Two conditions. One is 3k is greater than 0, and also 3k into k plus 2 minus 4 divided by 3k also should be greater than 0. Then only we can say the system is stable. So from this nonlinear equation, I can get k is greater than 0. And from this nonlinear equation, if I send this 3k to this side, then I'll be getting 3k square plus 6k minus 4 equal to 0. 3k square plus 6k minus 4 is greater than 0. So then find out what is the k value for this. That is by using k is equal to plus or minus root of minus b plus or minus root of b square minus 4ac by 2a. Use that equation. I'll be getting around k minus 0.5275 into k plus 2.5275. If we keep in the calculator, then it will be easy to get these roots. So this should be greater than 0. Next is, see here, if I want to is positive, then this k minus 0.5275 should be greater than 0, and k plus 2.5275 greater than 0. So from this equation, I can say k is greater than 0.5275, and from this equation, k is greater than minus 2.5275. So here the k is greater than 0. So all the values of k which satisfies the equation is, all the three ranges should be satisfied here. So common range we need to find out. So k is greater than 0, k is minus 2. So minus 2 to 0, it will not be satisfied. Okay, so we have to take k is greater than 0 and k is greater than 0.5275. Means for any value of k is, that is 0.5275 and more, then it is going to be, so this one will be taken into consideration by leaving this and by leaving this. Then I can write this range of k, the range of k, that is 0 less than k less than, sorry, not 0, infinity. So I can write infinity. I can write, no, not 0. Means k is greater than 0.5275 in the sense minimum range is going to be 0.57, 0.5275 less than k less than infinity. Less than infinity. So I can write. So k is greater than 0.5275, means for any value of k greater than 0.5275, the system is going to be stable. The system is going to be stable. So this is the range of k. Likewise, you can find out even the what you call marginal stable system. Marginal stable system, that is also, that is k will become, k marginal will become 0.5275 if you calculate that by using that equation, row of zeros concept. So 3k into s square x square plus 4 equal to 0, like that you can find out, and then let me know that k marginal value also. So this is how the relative stability with respect to the line can be calculated. With respect to the line can be calculated, right? So one more problem we can pick up here. The determine the location of roots with respect to s minus 2. Of course, you can write yes. One more problem you can take. Yeah. So this is here using the Routh array. Using the Routh array, we have found out the system stability, and also we have found out the range of values of k, and also we have found out the the relative stability of the system, for the range of values of k. So similarly, if I give a just open loop transfer function, so by applying Routh's criteria, discuss the stability of closed loop transfer function of k, which is having the function of k, and the following open loop transfer function is given, that is g of s into h of s is given. So that is g of s into h of s is given as k into s plus 1 divided by s into s minus 1 into s square plus 4s plus 16. So this is the open loop transfer function is given. Okay, so yeah. Right. So we need to find out the stability of the closed loop system. So discuss the stability here is asking about discuss the stability of this closed loop transfer function for the range of values of k. For the range of values of k, we need to find out. But he has given this open loop transfer function. So for any, if I want to use the Routh criteria, I need to have the characteristic equation. What is the characteristic equation? We have the characteristic equation is 1 plus g of s into h of s equal to 0. So that is the denominator of the closed loop transfer function is called as equated to 0, that is called as a characteristic equation. So from that, 1 plus g of s into h of s equal to 0. 1 plus, we know that g of s, h of s is given, that is 1 plus k into s plus 1 divided by s into s minus 1 into s square plus 4s plus 16 is equal to 0. So this will give the characteristic equation. So then simplify this equation, I'll be getting s square minus s into s square plus 4s plus 16 plus ks plus k equal to 0. Then multiply this s square term with a second factor, that is s to the power of 4 plus 4s cube plus 16 s square minus s cube minus 4s square minus 16s. So that is the expansion of these two terms. Then plus ks plus k is equal to 0. Then combining the terms, here if you look at, we have s to the power of 4, only one term is there. So I'll be writing the s to the power of 4. Then if you look at s cube terms, there are two is there, 4s cube minus s cube. Plus 4s cube minus s cube is going to be plus 3s cube. So plus 3s cube. Then second term, if you look at here, 16s square plus 16s square minus 4s square plus 16s square minus 4s square is going to be plus 12s square. Okay. Then one more is s terms. So if you look at the s terms here, we have the minus 16s and plus ks. So I can write k minus 16 into s, right? So plus k minus 16 into s. Then the constant term is plus k equal to 0. So this is what we have got the characteristic equation after the simplification. Now I'll form the Routh array now by using this characteristic equation. That is by writing this s to the power of 4 and s cube, then s square, then s to the power of 1, then s to the power of 0. S to the power of 4 and cubes, these two rows will be filled with this characteristic equation only. So when you write this, that is 1 and 3. 1 and 3. The second one is, I'll write a bit far here. So 12 and then k minus 16. Then one more is k and then 0. Like that, it will keep going with the zeros, right? Next is this into this, 3 into 12, 36 minus k plus 16. 36 minus k plus 16 is going to be 26 minus k. So straight 36 minus of minus plus, so plus minus k plus 16. So 36 plus 16 is going to be 52. Directly I'm writing 52 minus k divided by 3, and this into this 3k minus 0 divided by 3. So 3k minus 0 is 3k. 3k by 3 is going to be k, and then this is going to be 0. Next, this term is 52 minus k. I can write 52 minus k into k minus 16 minus 3k divided by, of course here it is 52 minus k by 3, and here also 52 minus k by 3. So this into this minus this into this divided by this, then this into, so this will become row of zeros, this will become row of zeros, and s to the power of 0, this into this minus this into this will become 0, this into this will become 0, this into this will become 0. So this term will be eliminated. So multiply only these two terms and then divided by with this term. So I'll be getting k. Here. Okay. So now if you look at this according to the Routh's array, the necessary and sufficient condition, the first column elements should have the same sign. Means plus 1 plus 3. So this also should be positive, this also should be positive, this also should be positive. So based on that we can write the range of k values. So first one is from this k is greater than 0. Then from this I can write 52 minus k by 3 is also greater than 0. And this, if I simplify this, 52 minus k into k minus 16 minus 9k is greater than 0, because this 3 is also multiplied here, I'll be getting minus 9k is greater than 0. So these are the three ranges which you can get. So k is greater than 0. Here if I look at the k, 52 minus k is greater than 0. 52 minus k is greater than 0. So 52 is greater than k, or I can write k is less than 52. So this is one more range, and from this I'll be getting a second order equation. That is, if I multiply this 52 and so on, so I'll be getting 52 into k, 52k minus 52 into 16, 16 to the 32, 832 minus k square minus into minus plus 16k minus 9k is greater than 0. So if I simplify this, I'll be getting minus k square plus 59k minus k square plus 59k, then minus 832 is greater than 0. So what I going to get here is going to be if this is greater than 0, if I want to get less than 0, I can multiply with the minus. So I'll get k square minus 59k plus 832 is less than 0, So from this equation, solve for k, I'll be getting the k is greater than 23.3153, and also k is less than 35.6846. So these are the k ranges which I can get. K is less than 52, and here if you look at k is less than 35 also. So it can take the value of a common range. If I take the common range, so the k lies, so from 0 to k is less than 23.3153, because the k is stable for the value of k is greater than this and then less than this value. So for any value of this 0 to k 3153, the system will become unstable. So here for this range only the system is stable. So for which range of the system is going to be stable? That is, the k is greater than 23.3153, means 23.3153 less than k less than 35.6846. So then in this, the system is said to be stable in nature. Now for any value of k is greater than 35, for any value of greater than 35.6486, then the system is said to be unstable. Unstable. 35.6846 is also unstable. And for k equal to any value of these two, lower limit of and upper limit of stability, lower limit and upper limit of the stability, that is for k is 23.3153 and k is equal to 35.6846, means it is on the verge of instability. That is nothing but marginally stable systems. That is a marginally stable system. Means it just, if it is trying to decrease the value of 23.53, and also when you are trying to increase the 35.6846, then it leads to the instability. See here, it leads to the reducing the 23.31153, then it will become the instability, and increasing the value of k more than k 35.6846, it will become unstable. So for the values of k equal to this and equal to value, then it is a marginally stable system. So this is how we need to find out the range of values of k, for which values of k it will be stable, and for which values of k it is unstable, and for which value of k it is marginally stable. So with this, I'll stop today.